Howdy, everyone. Welcome to Chapter 6, the electronic structure of atoms, where we get into some quantum mechanics, some electron configurations, all the good stuff when we talk about what makes an atom tick, what makes it have certain properties, and so forth. So we're all about electronic structure. Where are the electrons? How much energy do they have? But we're going to start talking about light. We're going to talk about waves. Because it turns out with electrons, we have to talk about them as if they were waves a lot of times. So just some basic information, just refresher from a physical science course or whatever. Electromagnetic radiation, light, moves as waves through space, right? It's a self-propagating wave. It just keeps going. And so every wave will have a wavelength, from top to top or trow to trow or what, just from the same point to the next point on the next wave, that's the wavelength. We also have a frequency where they say if you pick any point, how many complete waves go through any second. So that's here. Number of waves passing through a given point is the frequency in a unit of time. So we usually use per second. Doesn't have to be. And so waves that are traveling at the same velocity, if you have a longer wavelength, then you have to have a shorter frequency because you can't get as many waves through in the same amount of time. But here, when you have a shorter wavelength, then you have a higher frequency. You have more waves along this same segment here. And so it says if the time associated with the lines left is 1 second, then we have 2 versus 4 hertz, right? Reciprocal seconds is the hertz. So this says, I get through 2 complete waves in 1 second. Here I get through 1, 2, 3, and 4 in this 1 second segment of time. So wavelength and frequency are dependent on each other if it's the same wave, if it's the same stuff. So with electromagnetic radiation, light, it goes all the way from gamma rays all the way through radio frequency. Remember, visible light, just a small portion. And so since it all travels at the same speed, it all goes at the speed of light, 3.00 times 10 to the 8th meters per second. And that gives us this equation, which I believe does appear on the AP reference sheet, that the speed of light, c, is equal to the wavelength times the frequency. Remember, wavelength is this Greek letter lambda. Looks like the upside down Y or a kind of a turkey bone type thing. And then the frequency is given the symbol nu, which here it's kind of like a V. It's usually a V with a little bit of a curve to it, but sometimes they just put a V instead because it's easier to type. But if we look at the spectrum for a little bit, we'll talk about this. Remember, down here with gamma rays and X-rays and ultraviolet, that's the more energy. Radio waves have less energy. And visible light somewhere in the middle. That's why infrared, that's the heat we feel, right? Yeah, it can heat things up like microwaves, but it doesn't really do anything to us. Ultraviolet, that's more energy. That can give us skin cancer. X-rays, yeah, that can give us cancer. Gamma rays, it does not turn you into the Incredible Hulk. It just gets you, and then you don't come back. All right. So they tell us there that, because the wavelengths are obviously different along the spectrum, we'll often use different units for it. So nanometers is very important for visible light. We'll use that a lot when we talk about different colors of light. Angstroms, this one where it's not an SI unit because it's not based on the meter, but it's 10 to the negative 10th meters. It's this capital A with a circle. That one shows up more in bond lengths because most atom-to-atom bond lengths are on the order of angstroms. So carbon-to-carbon single bond is about 1.54. So since it's right about 1 to 2 for most bonds, angstroms gets used a lot for that. But it could also be used for X-rays. Millimeters, centimeters, there's microwaves, and even all the way up to kilometers for some radio. So they all have different wavelengths. They all have different energies. And the energy is going to be based on the wavelength, as we'll see here in a little bit. The issue is that there are properties of how atoms interact with light that don't get explained by saying light is a wave. It doesn't work. And so the 3 of them are black body radiation. When you heat something up, it starts to glow, right? That's where we get the term, it's red hot. It's so hot it's glowing red. Well, light as a wave does not tell you why that happens. It just doesn't work at all. Also, this thing called the photoelectric effect, that you have a piece of metal, you shine some light on it of a certain wavelength, and nothing happens. And then you change to a different color, and nothing happens. No matter how intense you make that beam of light, nothing happens until you switch the wavelength just enough, and then suddenly electrons start getting shot out of the metal. It's like, well, what's going on there? Why is it that no matter how powerful I made the light, it didn't happen until I changed to a certain color? And then the final one, emission spectra. That if you take an atom and kind of get into the gas phase and you zap it with electricity, you only see certain lines of light. You don't see every color, you don't see a rainbow, you only see a little bit of light, and only at certain colors, certain wavelengths. So waves don't explain this. These can only be explained by treating light as a particle, which we're then going to look at now. All right, so yeah, it says it doesn't do that. It says here for this thing about why does it glow red hot when it's heated up. It says Max Planck explained it by assuming energy comes in packets called quanta, which is true. This slide does nothing to explain it. It's a complicated equation. My favorite part, it involves the wavelength of light being raised to the 5th power, because squaring stuff or cubing stuff, it's kind of passé. But to the 5th power, that's where we're good. You don't need to know why it glows. Just it doesn't work with waves. It does work if you have individual levels of energy where you're either here or you're here. You can't hover in between the two steps, right? Flying is not allowed. You're only getting allowed certain discrete steps. And we call those quanta or quantum. All right? The photoelectric effect. This is what got Einstein his Nobel Prize. He used the idea of quanta, saying, oh, if we treat light as a particle, then certain particles will have enough energy to make the electrons fly out. But other ones won't have enough energy. No matter how many of those particles there are, if each individual particle doesn't have enough energy, it doesn't happen. So he got this equation of E equals h times nu, so that's the frequency, and h is Planck's constant, after Max Planck, 6.626 times 10 to the negative 34th joule seconds. Notice it's joule times seconds, not divided by. So there, if you have joule times seconds, and then your frequency is reciprocal seconds, the seconds cancel out and energy is in joules. So he said, oh, depending on the frequency of the light, or in other words, depending on the wavelength of light, depending on which way you look at it, either it has enough energy or it doesn't. So that's where you can figure out, well, how much energy do I need to kick out these electrons? That tells me which frequency and wavelength I need. All right? And the last one, these atomic emissions, where here neon shows up orange, and hydrogen kind of shows up this purple color. Well, why are they different colors? If you break this down with a prism, you see a bunch of lines for this, but most of them in the orange. Hydrogen, you only see 4 lines, and they're spread out. There's some red, there's some blue, there's a purple. How does this make sense? And so this is where we're going to talk about a continuous spectrum versus a line spectrum. If you have a pure white source, like, well, here they have a flashlight, but that's not always good enough. Depends on what type of flashlight. But let's say, I don't know, the sun. If you put it through a slit so that only a straight beam of light goes through, and then you put that through a prism to split the light, you will get a full rainbow. That is what we mean by a continuous spectrum. You get every color, it all merges from one to the other. That's the continuous spectrum. But if you do that same thing with the emission tubes, if you take these tubes and hold them up to the slit and then pass that light through a prism, well, here's hydrogen, purple, purple, blue, red. And it's always those 4 lines. It's always those 4 lines in that exact spot. For neon, here we'd say, well, why was it more orange? Well, there's a little bit of blue, a little bit of green, but mostly yellow, orange, and red. And because there's so much more of this, overall we see orange when it's all combined. And so it says here, each element has a unique spectrum. This is how we sometimes call it, we fingerprint elements, where, especially for astronomy, if they say, oh, we've detected this element or this compound or this whatever out in space, they're using this stuff. They also use hydrogen, since that's the most abundant element in space, whenever they say, oh, this galaxy or this star is moving towards us or away from us at some speed. Well, how do they figure that out? Well, they know where the lines for hydrogen should be, and if the star is coming towards us, that's called the blue shift Doppler effect. Things get shifted more in the blue-purple region, and so we know the calculations say, oh, if the hydrogen lines show up off a bit, we can calculate how quickly that star is coming towards us. And if the star or galaxy or whatever is moving away from us, well, then these get redshifted. They move more to the right. And again, we can use the equations from physics to say, oh, well, this is how far it must, how quickly it must be moving away from us in order to show up in those spots. So this stuff, even though it's kind of old chemistry and old physics, still gets used every day in certain fields because what's the easiest way to do it? How else are we going to tell how far away or how fast a star is moving when it's halfway across the galaxy? All right. So this hydrogen spectrum, people knew about it for a while, right? Okay, we always get these same 4 lines. Well, these 4 lines end up being called the Balmer series because Johann Balmer in 1885 figured out a formula that would relate them to integers, whole numbers. And then a little bit later we have Johannes Rydberg, who kind of refined it a little bit and came up with this equation, that 1 over the wavelength would be equal to a Rydberg constant times 1 divided by n1 squared minus 1 divided by n2 squared, where n1 and n2 were your 2 energy levels given by these integers. So if it's the first energy level, so 1 over 1 squared is 1. The second energy level, that's 1 over 2 squared is 1/4. Okay, 1 minus 1/4 is 3/4. If you do 3/4 times the Rydberg constant, that would let you calculate, well, what wavelength of light should I see going from the second to the first integer? It turns out actually for this Balmer series, all these lines are going from some higher integer to the second. So this should be the 3rd level to the second. This will be the 4th level to the second, the 5th, and then the 6th level to the second one. That's the Rydberg equation. He figured that out. And then along comes Niels Bohr from Denmark explaining, why does this equation work? How is the atom put together with the electrons and the protons and all these lines of light? How much must that tell us the atom is put together to make it all work? So his model takes Planck's idea about energy being quantized, takes the Rydberg equation, takes all the other stuff, and combines it to say, okay, these electrons, they must be in orbits of certain radii, which matches up to a specific certain energy. And only those certain energies are allowed. So we can be at this energy level 1, or we could be at energy level 2 or 3 or 4, but we can't be anywhere in between. Electrons are not allowed to be here. If they're anywhere in between, they'll just fall down until they get to a spot they're allowed to be. All right? And if they end up 2.5, well, then they'll fall down until they get to 2. But they are not allowed to stay anywhere in between. All right? So it's only permitted there. An electron in the allowed state does not radiate energy, and it does not spiral into the nucleus. So the idea there is just trying to say, like, well, how come if an electron's negative and the nucleus with all the protons is positive, shouldn't all the electrons just fly straight into the nucleus? Shouldn't they all just go as close as they can? And he said, no, they have to stay in this allowed energy, otherwise it just doesn't work. The atom falls apart. And then his third part, energy emitted or absorbed only happens when an electron moves from one allowed state to another. So from state 1 to state 2, that's a certain amount of energy. State 2 back to 1, that's the same amount of energy, just it's going to be released instead. And there's a certain amount of energy from 1 to 3, or 3 to 1, or 3 to 2, or 3 to 4. There's only allowed to be those certain amounts of energy, and those amounts are what we see here with this E equals h nu. Those energies are how we figured out, well, where do I put ground state 1? Where do I put ground state 2, state 3, state 4? That's where he got these energy levels from, by looking at, well, those lines. How much energy do those lines have? Bohr ended up winning the Nobel Prize the year after Einstein did for the photoelectric effect. So you can see here, there's a lot of good science being done in a very short amount of time. All right. The lowest amount of energy, this lowest one, we call it the ground state. Any state above it is an excited state. And so this is more for hydrogen. But for any atom, if we kind of generalize it, if the electrons are in the lowest orbitals that they're allowed to be, then that's considered the ground state. If any electron is kicked up to a higher level than it's supposed to be at, that's considered excited. Right? And so here's how Bohr did it. He took that Rydberg constant and the equation and said, oh, well then it's not just going to tell me what the wavelength of light is, it's going to tell me my delta E, my energy difference between these. And when he looked at the different colors of light, he was able to say, oh, okay, this shows up. Now I said the Balmer series goes to this second energy level from 3 to 2, 4 to 2, 5 to 2. That's because these that go all the way down to 1, you can see that's a much greater energy. It shows up in the ultraviolet, and we just can't see it. So this one here that goes from about 6 to 2, that's the purple line we see, and that's about as far as we go. If we go to higher levels, we can't really see it too great. All right, so what do these values mean? Kind of what we said earlier here. If we have a positive delta E, energy is absorbed. A photon, a particle of light, is absorbed. So I'm realizing that this PowerPoint kind of skipped over photons when they said, oh, you can't explain everything with waves. Well, what's the particle part? A particle of light is called a photon. So we're saying a particle of light gets absorbed, the electron jumps up an energy level, and there we go. A negative delta E means energy is released, and that means, well, where's the energy go? It's released by an emitted photon. So when the electron drops from, say, 2 to 1, that amount of energy comes out as a photon of light. Maybe it's light we can see, maybe it's ultraviolet and we can't see it, but that's the light that comes out of the sample. All right? Now here's the problem with the Bohr model. It only works for hydrogen. It works perfectly for hydrogen. Those equations are spot on. Everything's great there. But it doesn't work for helium. As soon as you add that second electron, it doesn't work. Lithium gets even farther off. We say here the classical physics assumes that electrons would go to the positive nucleus, right? Why don't the opposites just snap together? Bohr says, no, I have a reason to believe it doesn't because we kind of have this evidence that it doesn't. And Bohr said it was circular motion. He gave it a radius. Turns out electrons need to behave more like waves in order to get all the behavior we've got, which is kind of weird that we just said we have to treat light as a particle and as a wave. But now electrons, which are particles, and definitely are particles, well, we have to kind of treat them a little bit like waves too. This is what we call the wave-particle duality. So it's, sometimes it's easier to think of it as one way or another. But these are the important ideas from Bohr's model that we still use. We still say electrons exist in discrete energy levels. They're allowed here, they're not allowed anywhere in between. These energy levels are described by quantum numbers, which we'll get to in the next video. And the energy that is involved, that light that's absorbed or released, is the energy from an electron transferring from one energy level to another. All right. Well, how do we talk a little bit about this particle stuff? Well, this gets us to this guy. As an American, we would say Louis de Broglie. I looked it up. It's more like Louis de Broglie, or Broglie. I'm not French. I'm sorry for anyone who speaks French if I just insulted you. I'm going to go American now. Louis de Broglie. He said, well, wait a minute. If light can act like particles, maybe particles can act like light and be like a wave. And so he came up with this pretty simple equation that says the wavelength of a particle is equal to h, that same Planck constant again, it shows up lots in this chapter, divided by the mass of the particle times its velocity. Well, mass times velocity is momentum. So he was saying, hey, I can relate the wavelength of a particle to its momentum. If I have a really large momentum, then I will have a really, really tiny wavelength. It'll be lots of energy. If I have a very, very small momentum, because of a very, very small particle or a very, very small velocity, well, then I can have a bigger wavelength, a wavelength that might be more measurable. Right? And so we can kind of see this. We use these electron, I think it's a scanning electron microscope here, an SEM picture, it could be TEM. But they use the fact that electrons act as waves in order to kind of map where are the electrons here. So this is, from what I can tell, a sheet of graphite. And so they're kind of saying, well, graphite, we say, looks like hexagons. Why do we say that? Because we look at this and we say, yeah, it looks like hexagons. Because the wave nature of electrons helped us see this, of where do they bump into the things and where do they not bump into things. All right. The last thing we'll talk about here in this part of the video is the Heisenberg uncertainty principle, which is something that lots of people talk about and very few people understand. because they always say, oh, you can't know the mass and velocity, or sorry, the position and the velocity of things at the same time. And they're right. But Heisenberg actually had a more general one, which said, well, it depends on what two things you're looking at. But if the two, what we call operators, if they interact in a certain way, then they also are uncertain. It's not just position and velocity, but that's the main one that we talk about. But again, it actually isn't just velocity. It's, again, mass times velocity. That's momentum. So what he really said was the uncertainty of position, right, this delta x, how plus or minus is your position, times the uncertainty in your momentum, plus or minus, how far are you, must always be greater than or equal to Planck's constant, again, divided by 4 pi. And so this is actually a really small number, right? Planck's constant was 10 to the negative 34th joule seconds. That's a teensy tiny number. And then you're dividing it by even more, so it's getting even smaller. But then we have to remember, the positions we're talking about for electrons are really, really tiny, right? I mean, we said a bond length is about 10 to the minus 10th meters, so individual electron positions even smaller. The momentum, the mass of an electron is really tiny. It's in 10 to the minus 27th, I think, kilograms. So that's actually not too far off from the Heisenberg. And then its velocity. It's not moving all that fast on a large scale with meters per second. So these numbers end up being very, very small as well for an electron. And so when you take a very small number times a very small number, it actually does bump into this pretty quickly once you get down to a single electron. So it does say we can know its position really well, but because this uncertainty must be greater than this ratio, that means this momentum term must get bigger, the uncertainty in the momentum term. Or if we know the momentum really, really well to a very small uncertainty, well, then its position must be much more uncertain to keep this inequality true. All right, we're going to stop there for this video because we're going to say, okay, if we put all this stuff together, the Bohr model that works for hydrogen but not the other stuff, de Broglie's wave-particle duality of an electron or of matter, Heisenberg saying, well, there's some uncertainty in things of how we can put things together. We're going to bring in a guy called Schrodinger, and we're going to put it all together to say, what the heck does an atom look like? Where are the electrons? Where are they allowed to be? How does it all work? All right, so join me next time for that.